Hi everyone, my name is Matt Chopin, and today I'm going to present a paper, Passage-time distances, geodesics, and barycenters of mesh trees. Let's say we have two scalar fields in 2D. The third dimension represents the scalar value here. This data represents four mountains that are very similar. The only difference is that we have swapped the two small mountains here and there. For each scalar field, we can compute the persistence diagram, a classical representation in topological data analysis. It summarizes the features of interest in the data. Here, the four mountains are summarized to the four bars, whose lengths are proportional to the corresponding mountain's height. Unfortunately, it can lack in discriminality. Here, the two persistence diagrams are the same, whereas the data are different. It is because it informs us about the presence of the mountains, but not how they are connected together. To tackle this problem, we can use a more sophisticated topological abstraction called the mesh tree. This object will inform us, like the persistence diagram, about the presence of the four mountains, but also how they are connected together, giving here two different mesh trees. It can be very useful in practice to perform the analysis on the topological data representations instead of the original data, in order to overcome I/O limitations, for instance. For this, we need a statistical analysis framework for mesh trees like we have for persistence diagrams. We need to introduce a few tools, such as distances to compare them, geodesics, as well as barycenters to have a mesh tree representative of a set. We can see a persistence diagram as a set of 2D points. The passage-time distance between them can be defined as an assignment problem, where we'll assign to each point of the first diagram a point in the second one. We can also insert or destruct a point that is symbolized by a matching with diagonal, like we can see here. In the work of Turner et al., a geodesic between persistence diagrams is defined as an interpolation of the matching points in this 2D space, like we can see in this interpolated diagram. The metric between mesh trees was proposed by Sundaramurthy et al. Based on the edit distance. However, the simple interpolation of the matched nodes does not result in geodesics or shortest path, in contrast to our work. A method was proposed to find one center, a mesh tree that minimizes the maximum distance over a set of mesh trees. However, by definition, one centers are sensitive to outliers, like we can see here. We took 10 noisy versions of the same scalar field, and we had one outlier. In contrast, we introduced in this paper barycenters of mesh trees that minimize the sums of distances and which consequently better capture overlay chains in the ensemble. In this work, we propose a new method to compute distances between mesh trees that are purposely designed for the efficient computation of geodesics and barycenters. It constitutes a unified computational framework implemented in a single clustering algorithm that generalizes the barycenter program as well as the geodesic and distance program. We show the utility of our approach to ensemble analysis and visualization applications, and finally, everything is available, including an open source C++ implementation. The proposed metric is based on the edit distance between mesh trees that we modify to allow simple geodesic and barycenter computation, and also to have a clear relation with the passage-time distance between persistence diagrams, as we will see. The first thing is to use as input the branch decomposition tree representation, where each node is a persistent pair or a branch and no longer a critical point. By doing so, the matching will involve the persistence pairs like in the persistence diagram. Then we modify the formulation of the edit distance. The idea of the latter is to use edit operations such as relabel, deletion, and insertion to transform one tree to another. Each operation has a cost, and the edit distance aims to find the lowest total cost. We formulate the edit distance as the two passage-time distance between persistence diagrams. They then become equivalent. The only difference is that we have a smaller solution space because we use the structure of the tree to forbid some matchings. In addition to the constraint of the original edit distance that disjoint subtrees need to map to disjoint subtrees, we extend this by constraining the destruction of an entire subtree if its root is deleted. This will help efficient geodesic computation by a simple interpolation. Finally, we use as cost of the edit operations the same as the L2 passage-time distance between persistence diagrams, being the Euclidean distance in the birthday space. The algorithm used for distance computation is based on the dynamic programming algorithm of Zhang. The first step is to compute for each subtree its distance to the empty tree. This can be easily achieved by starting at the leaves and summing the deletion cost of each node while going up in the tree. The second step is to compute the distance between the first tree and the second one. We define the distance between the subtree with bhi as a root and the subtree with bg as a root, as the cost of transforming the node bhi to bg, plus the cost of transforming the forest of bhi, so these subtrees, to the forest of bg. The distance between two forests is actually an assignment problem between their subtrees. The costs involved in the assignment problem are the previously computed distances between the subtrees at a lower level and the distances to the empty tree. This is a recursive definition. The black term here actually corresponds to the distance between BDT of this term. In practice, we start by processing the leaves of the first tree, then we process a node when all of its children are finished. Each processing is saved in a table to be used later. The processing of a node in the first tree consists in computing the distance between its subtree and each subtree in the second input tree. Since we had the constraint that subtrees are destroyed if their root is, only subtrees at the same depth level should be considered. Each processing of a node can be done in parallel, and the only dependency being the ancestor relations between nodes. We need to process all children of a node before processing it. The second main contribution of our work is the geodesic computation given a new metric. It is based on the interpolation used with the persistence diagrams. An important problem is that the direct interpolation of the matched branches can result in an invalid merge tree. In particular, when a pair is destroyed in above the space, it is considered to be matched to a point of average scalar value, like we can see with the red point here. We can see here that if we do this naive interpolation, the small dark pair will be out the range value of its parent, giving an invalid merge tree. Specifically, we will want the pair to stay in the range of its parent, like we can see here. This is a mandatory condition to have a valid merge tree. It can be called the nesting condition, stating that the range value of a pair must be in the range of the ones of its parent. To guarantee that an interpolating merge tree will always respect this condition, we can use a local normalization. This is actually a min-max normalization, where we normalize the scalar values of a persistent pair to be between 0 and 1 using the scalar values of its parent. We can show that the solution to an interpolating pair in a geodesic is an interpolation between the normalized match pairs, which is between 0 and 1, then followed by the inverse normalization, which rescales the interval to the 1 of its parent, hence guaranteeing the nesting condition. The geodesic solution can be generalized to more than 2 trees to compute the barycenter. We use a variant of the algorithm of Turner et al. For persistence diagrams. It consists in 2 steps that we repeat until convergence: assignment and update. At first, we initialize the barycenter candidate. Then the assignment step computes matching between the barycenter and each input tree. Next, the update step consists in moving each branch to the arithmetic mean of the matchings. We can also extend this to a clustering algorithm by generalizing the barycenter method to more than one barycenter called centroid. It is a variant of the k-means algorithm that consists also in 2 steps, assignment and update. At first, we initialize the centroid. Then, in the assignment step, we compute the matching between each centroid and each input tree. Finally, in the update step, we apply the barycenter algorithm above to each centroid with the trees assigned to this cluster. At first, we have measured the execution time of a barycenter using a proposed method in parallel and sequential. It is done on some datasets, including some Sybase contests. In terms of the number of persistent pairs, we have a wide range from very small datasets with some 100 pairs to bigger datasets with thousands of pairs. The number of members in each ensemble varies in the order of tens. And finally, the parallel execution time go from some seconds for the smallest datasets to some minutes for the bigger one. Since the publication, we have even improved the implementation, and we are now in average 3 times faster. We empirically evaluate the stability of the proposed metric using a scalar field with a random noise of increasing amplitude. This is done for different values of epsilon1. This parameter, introduced by Sridharamurthy et al., controls the structure of the tree by magic saddle points when a difference in function value is below epsilon1. On the branch decomposition, it has the effect to bring up pairs in the tree hierarchy. When it is set to 1, the structure of the tree is not taken into account, and the proposed metric becomes strictly equivalent to the Wasserstein distance between persistent diagrams. In that case, the distance evolves linearly with the noise, which is expected given the stability of the Wasserstein distance between diagrams. For lower values, the structure of the trees comes into play, and we can see clear transition points for which the metric still remains stable in practice before. Overall, we see that this parameter can control the stability and that even for small values, the metric remains stable under reasonable noise levels. The first application of our work uses the matching of the proposed metric to track features over time. We use here the ionization form dataset. It corresponds to the concentration in ions expelled by a star. On the left, we see the matching given a persistence diagram. Since it considers persistent pairs individually, it can produce incorrect matching with crossing in the tracking. On the right, we see the matching of the merge trees that works better since the structure of the tree constrains the matching by exploiting the global structure of the data. The second application uses the geodesic for subsampling a sequence of merge trees. We use here the asteroid impact dataset. The idea is to really remove trees from the original sequence that can be accurately reconstructed with the geodesic computation for the purpose of data reduction. This iterated removal reveals the keyframes of the sequence that are used to automatically reconstruct the removed frames with the blue background. These keyframes correspond to key phases in the asteroid impact: the initial state, the approach, the impact, and finally the aftermath. When using persistence diagrams, the method fails at capturing the impact phase and select two keyframes in the aftermath phase, as we can see in the red curve. Finally, we can use the clustering algorithm to see the main trends in the ensemble dataset. Here we use the dark sky dataset that represents the evolution of the concentration of dark matter of the universe over time. The algorithm correctly assigns the members to the right clusters given a ground truth classification. The computed centroids provide a visual summary of the main features of interest present in each cluster. Each feature in the centroid can be related to a feature in the data of the cluster using the matching. Then the centroid can also act as a visual reference for the members in the cluster to relate features together. For example, in this first cluster, we can see that these big blue branches are matched together in the centroid, and therefore we can see in the field that the features are related. To conclude, this work presents a new metric between merge trees that is discriminant and stable in practice. Thanks to the relation with the passage-time distance between persistence diagrams and the local normalization, we can use a simple interpolation to compute geodesics. This work proposes the first method to compute barycenters and clustering of merge trees, and we show the utility of our approach with various applications to ensemble data analysis. Finally, everything is available. The code and some examples are present in TTK. The paper is replicable. It has been awarded the replicability stamp. And the exact code used for the paper and the created data are available in these GitHub repositories. This work report is partially supported by the European Commission grant TORI. And thank you. I will be happy to answer questions.